Okay, so good morning, everyone. Thanks for joining in this Saturday morning. And today, Souvik Sasmal is our speaker, and he works in the crystallographic lab, as you know, headed by Professor Thamizabal. So before beginning, let's give a short introduction of Souvik. So he did his bachelor's in Vidyasagar University, and later he moved for his master's in IIT Madras. And since then, he has been working and making some fantastic crystals actually in Professor Thamizabal's lab. So we are blessed kind of to have him as our speaker today. And stage is yours, Souvik.
Thank you, Subhajit, for this nice introduction. So I am Souvik Sasmal. Actually, my main focus of research is growing large size single crystalline material. So today's in these talks, I'll show you some interesting electrical and magnetic properties in Dirac semimetal europium copper-2Sb2. So you can see this is the crystal structure, and this dark brown color is basically europium atom, and these europium moments are aligned antiferromagnetically in AB plane, and this crystal structure has unique properties due to this europium moment present in the crystal structure. I will come to the brief the properties and observed electrical transport measurements. So let me start with the content that I put in this talk. That we first go to introduction, then we'll talk about the crystal growth part, then basic characterization such as X-ray diffraction, then magnetic and electrical transport measurement, and at the end I'll show you some ARPES data which reveals the presence of Dirac like linear band crossing near the Fermi level. So initially we work on calcium copper Sb. It has a unique hexagonal structure which has basically insulating these calcium layers are separated by metallic copper Sp layer. So this metallic layer has great significance in electrical transport, showing some kind of 2D nature. Then we were thinking of replacing this calcium atom with some magnetic element. So we thought that why don't we replace this calcium atom with europium atom? So later on we established this europium copper-2Sb2, where actually these europium moments are aligned antiferromagnetically, and these moments basically enhances its transport property in the sense it shows more peculiar type behavior in this in europium copper-2Sb2. And this europium moment has spin state has state of 2+, which gives us the spins of 7/2 moments. So how we grow this europium copper-2Sb2? So initially we take europium copper and Sb in 1:6:8 molar ratio in an aluminum crucible. Then we seal that aluminum crucible in a quartz ampule in this shape. So this shape is important for a different purpose that I am not going. But the point is that how we take these systems in a furnace and we follow temperature profile like this. So first we increase the temperature to 1050, where we stay there for 24 hours. Then we slowly cool down the system to 700, and where at that particular temperature we centrifuge, and after centrifuging we have excess amount of copper Sb, which is used as a flux, can be removed. So this is how we grow this europium copper-2Sb2. So you can see this nice face set type crystal, and it has a size of like centimeter size. That is good size in crystal growth. So this is the crystal structure. So unit cell of europium copper-2Sb2. So you can see it has small A axis and it has large C axis, and this is tetragonal structure. And these europium moments are basically antiferromagnetically aligned, and they are separated by this copper Sp layer. Now, to understand that, we have to check the quality of grown material. So first we check whether the grown sample is single crystal or not. So by doing diffraction pattern, we can see the crystallographic axis along C axis or A axis. We can identify particular crystallographic axis, and we can cut along particular axis, and we can understand their electrical transport measurement and magnetic measurements, applying field along particular direction. And our X-ray diffraction pattern also confirms that the grown sample is europium copper-2Sb2. And the lattice parameter here also I have given that A-axis is 4.4 angstrom and C-axis is 10.7 angstrom. So first we can apply magnetic, as I already told, we can cut crystal along particular crystallographic direction so that we have measured for field along A direction and field along crystallographic C direction. So you can see for B parallel to B means here the magnetic field. When we apply magnetic field along A axis, we see the magnetic susceptibility shows the antiferromagnetic transition temperature at 5.1 K, and it has basically very small FC ZFC bifurcation because of some kind of antiferromagnetically preferred orientation. So this happens because you can see this AB plane has moment along this direction, and this European moments has this direction moment along oriented along this direction. So when we apply magnetic field along A direction, this kind of one plane is acting like ferromagnetic layer, and this is acting like a ferromagnetic layer with opposite moment direction, and this also again other moment direction. So due to this one, we have seen some kind of small bifurcation between ZFC, FC. In general purpose, antiferromagnetically don't show bifurcation, but due to kind of some kind of antiferromagnetic domain present in this case can lead to this small bifurcation. Whereas when we apply field along C direction, means
so Souvik, one small question, sorry.
Yes,
so you can identify this A and C axis by diffraction, is it?
Yes, Laue diffraction pattern.
Okay.
You can see this pattern is completely different for C and A. So this is how we identify. Yeah. Yes.
Okay. And like in the next slide, which you are showing. So let's say for 500 Oersted data, there seems to be a saturation with temperature, right? Which is not the case for other data.
So 5, yes. So this goes like this, and other goes. So this is ZFC. FC means we measure in page. So what we do first, we take the sample, take the sample temperature to a very low temperature. Then we apply magnetic field. Then we measure the magnetic moment as a function of temperature. So it goes like this. Okay. Then we come back again. So that time the field is present itself. So initial case there was no field. Then we applied. Then we measure up to high temperature. Then we come back. Again we start measuring. So while measuring the second time, the magnetic field present in that case also. Yes.
Oh, so why is there a difference in temperature axis? Means depending on the direction of the temperature, means up direction and down direction.
This bifurcation.
Yeah.
So generally it shows in ferromagnetic material. So in ferromagnetic cases we have domain. So initially when we at low temperature but there is no field, so they are aligned along particular direction. Let's say moments are. Now we increase the we certainly then apply magnetic field. Then spins are oriented. Okay. Then we measure magnetic moment as a function of temperature. But the second time what is happening in that cases, when we returning back to lower temperature, that time the field is present itself. Okay. So domains are already aligned so that the moment is higher to the earlier one. But this case is antiferromagnetic. So in this cases, there are few material antiferromagnetic materials also. So basically, this kind of very small bifurcation because of the antiferromagnetic domain. So as I already told, this plane you can think of like ferromagnetically aligned along one direction, and this is like ferromagnetically aligned along this direction.
Yeah.
And this is so you can think of like that. Yes.
Okay. Okay. Thank you.
Yes. So then we measure the magnetic moment as a function of magnetic field, which basically try to saturate at higher field value, and showing some kind of 7 mu v moments at high magnetic field. Although it has not been saturated, we need more magnetic field to saturate it. So coming back to the resistivity, you can see the as I already told that our magnetization data shows the antiferromagnetic transition at 5K. Similarly, you can see at zero magnetic field, the resistivity as a function of temperature shows the same antiferromagnetic transition at 5.1K. And when we apply magnetic field more and more, the moments are try to align along C direction. So here current is along A direction, means we apply current, let's say, along this plane, and field is along C direction. So field has been applied along this direction. So in that cases, we are measuring this resistivity. Now, as we increase the magnetic field, you can see 1, 2, 3, 4. As we apply magnetic field along C direction, so these spins are basically try to orient along C direction. So they are basically started orienting with magnetic field. So as it started orienting with magnetic field, this transition temperature also goes down. So it goes down, and with very high magnetic field, let's say 4 Tesla, 5 Tesla, this antiferromagnetic transition basically vanishes. So you can see here I have shown the basically this field temperature phase diagram, and we basically separated with this dotted and this region with antiferromagnetic state and the paramagnetic state. So like up to 5K so at zero magnetic field we have the transition at 5K, and as we increase the field value, the transition temperature goes down. So this is how we identify this antiferromagnetic region, and which is the paramagnetic region. So as far as it's nice, now coming back to the magnetoresistance, means here we basically measure the electrical resistivity as a function of magnetic field. So first, let me tell you what we measure here. So we first take the sample to 2K, and we started applying field. So initially we are at zero magnetic field. Then we increase the magnetic field. You can see this blue line. Then it goes in this path, and we increase the field up to 14 Tesla. So it reaches here. So now you come back to these places. So initially what we do, we go from 0 to this value. So this anomaly or this hinge kind of behavior, you can think of that happened when my moments are try to align, and it has basically kind of like when the moment at particular A1 position, means while this position, we have kind of like spin canting happening, so that this hinge kind of behavior has been observed. Then it goes in this way. Okay, so we are now at 14 Tesla. Then when we come back from 14 Tesla via this A2 path, we see this difference. You can see this difference, path difference. So when it coming from then high value with this high 14 Tesla plus value to going to 0, then we see this spin canting at A2 position. So it comes with the different angular kind of canting of moment. And again, we go to from 0 to slowly to negative field. It goes via A4 path. And while coming back from the high negative value of magnetic field, let's say minus 14 Tesla to 0, it comes via A3 path. So this this difference in paths basically indicates the preferred spin counting in the systems which I have identified with indication of A1, A2, A3, A4. So this is the actually behavior in this particular cases. And more interestingly, we observe when we measure this Hall resistivity. So Hall resistivity, here I have shown Hall resistance as a function of magnetic field, which basically shows that almost zero Hall resistance. There is no actually Hall resistance. We have measured 4-5 samples, but there is no Hall resistance or Hall voltage. So we were so puzzled that why actually for particularly these cases, this Hall voltage is almost zero. You can see this, it has scale of micro ohm semi. And even if we go to the 10 Tesla also or 14 Tesla also, it is showing like in this a very small jiggling kind of things, but it is in the, we can think of in error bar, this is small jiggling. But the thing is, the Hall value is actually very small. So then we were searching for what could be the reason behind such such a negligible Hall resistance. Then we performed ARPES, basically angle resolved photoemission spectroscopy, where we with the photon energy of 134 electron volt, we see this linear type band crossing present at near the Fermi level. So this zero level is indicated as Fermi energy. So you can see this linear type band crossing. So I show you where clear picture will show you this here. So this is the zoom version of this basically. So you can see this linear type band crossing present in this case. And here is the raw data of intensity versus A parallel. And this from there we conclude some kind of Dirac state present in the systems. Later on, our DFT calculation also reveals that presence of this Dirac cone in these cases. Although the analysis are yet to complete, but the understanding is coming from, I show you one examples of which also shows similar kind of behavior. So here is European CD2AS2, which are known as topological wild semi-metal, and it shows also similar kind of linear band crossing near the Fermi level. And later on, we see this almost very low Hall resistance present in multilayer MnBi2 T4, and they claim that some kind of layer Hall effect could be the possible reason behind such observing phenomena. So particular that cases, they basically tells that it has Mn moment present in the unit cell. And when you have basically, let's say, so in this case, let's say I have 3 layers of MnBi2 T4. That means if my one layer is the one layer Mn moment is aligned along one axis, let's say A axis, then the second layer moment, Mn moment will align along minus A, and the third will align along A. So you can think of that, let's say 2 layers cancel each other, but one layer will stay hanging. That layer basically leads you to this kind of observation of this jump. But when we have 4 layers of this MnBi2 T4, we see this flat kind of Hall resistance. So basically that is kind of like cancelling this top and bottom layer of this Mn. And this red and blue basically identified with some kind of quantity that is called Chan number, but I'm not going that details. But this cancellation basically leads to observation of this kind of negligible Hall resistance in MnBi2 T4 at particular field. When they just process that field, basically that leads to again quantized Hall steps, and basically these are the quantized Hall steps. So coming back to our cases, so we were also thinking that in our case also some kind of this spin moment and the band topology leads to observing this kind of negligible Hall resistance, kind of like cancellation to surface state, basically each other, and yeah, observing this negligible Hall resistance in these cases. So at the end, I summarize my talk. So we grew this europium copper to Sb2 by flux method, and it shows europium 2 plus state and antiferromagnetically aligned, and the antiferromagnetic transition is at 5.1 K, and our ARPES result also shows that linear band crossing present at Fermi level, and overall the magnetism and the Dirac state present in this case results in such observing negligible Hall resistance and interesting transport. Thank you.
Thanks, Shovi, for the nice talk. So we have some time for questions. So if anyone has some questions, can ask. Unmute and ask. Yeah.
So I have one small question. So how do you directly measure the magnetic moment? So this is a direct measurement or some extracted
Magnetic measurement.
From magnetic moment, how do you measure?
Magnetic moment. So we measure the magnet in squid. Let's say we measure, we apply magnetic field and we look at the moment value. So we cut along particular crystallographic direction, and then we apply magnetic field, and in squid we can measure this moment.
Okay, so basically squid based.
Yes, yes, yes.
Okay. I had actually one question. So let's say layer Hall effect also gives Rxy is equal to 0, and if there is no such effect, like nothing is happening, no anomalous Hall effect, then also it's kind of Rxy is equal to 0, right? So how can one distinguish between these two effects?
Sorry, can you repeat?
So I am saying that let's say we don't have layer Hall effect. Okay.
Yes, yes.
Then also we can have in some materials, let's say Rxy is equal to 0, which don't have anomalous Hall effect, like no anomalous Hall, no layer Hall effect. Then also it's kind of Rxy should be equal to 0, right? So how can one distinguish between these two cases, whether if there is layer Hall effect or not? Because both have like layer Hall effect is basically cancellation and giving rise to
yes.
Yeah, how to contrary that with if in some cases nothing is happening.
Nothing means you see the negligible Hall resistance, still you believe that if there is no layer Hall effect.
Yes, if that is possible.
Yeah, actually this behavior has not been much understood. Actually, I cannot claim.
Okay.
Yeah, I cannot give a clear answer.
No, I was thinking of some like experiments. Can I annotate briefly? So yeah, I will annotate on the screen. So let's say I have one layer, like you grow layer by layer, multiple layers. Okay.
Yeah. Yeah.
Like one layer, and on top of that another layer. If in our case we can take two shapes of we can vary the shape by something called etching. So
okay.
So what we can do is we can shape one of the layers to have a like greater extent in one of the places, and in another place it's basically aligned with the upper layer. So I am drawing this dashed line. So above this dashed line, we have like in the upper layer, both the layers are kind of aligned. Yeah. And in the lower part, one layer is layer X extent is greater than the other. Yeah. Now, let's say I can have some probes like this, which only touches one of the layer. Okay, here, like either upper layer or bottom layer, and simultaneously in the upper region I also make probes which now touches both the layer. Now I was thinking like in the in the upper part, I will, in the same device, in the upper part, I will observe Rxy is equal to 0. But because it's a layer hole effect, if I touch only one layer, then the lower part should I see a non-zero value.
Okay.
Yeah, I was also thinking how to probe this with more concreteness, this layer hole effect, the new phenomena.
Yes. Actually, in
Yeah.
MNBI to TIFR, they measure like 3-4 stacking of material, and on top of it, right? They make contact, or
I think they make contact throughout, like the upper part I draw. I have to read that paper, but
think.
I don't think they have done like that. But
Okay.
yeah, we can read that and discuss more. But it's interesting measurements like new, I guess, in layer physics.
Yes.
Since if no one else have any question, like
Actually, this part is not explored much. I want to do.
Yeah, true.
Even this is completely new understanding.
Yes, true. So yeah, I was also asking, like, is there a way you can vary the magnetic field direction application angle with respect to current, like from A to C axis, can you continuously vary the angle of magnetic field?
Yes, actually we have measured the angular dependent magnetoresistance. So I can show you later. Actually, that
Okay, that's
I have
fine.
not put because I have not completely analyzed that one. But yes, that is also I can show you actually. Yeah.
So does anything like interest? I mean, I mean to say that how do you do it? Like you have a, like you can cool and rotate the angle while the device is cooled, or?
And so what we do, we have rotator. So we first take the sample and we cool down to 2K, let's say lower temperature. Then we apply magnetic field, let's say 4 Tesla or 2 Tesla. Then we rotate from along field direction. Let's say my sample is in like this. Then what we do, and field is along this direction and current is along this direction. Now we can rotate like this. So that we have also seen. And yes, actually, yeah, I can show you that one.
Okay, fine. Yeah, nice. And the rate of rise of temperature and slow cooling, that is very like slow compared to like our day-to-day experiments. Like it takes several days, right? You are quoting some 15 degrees centigrade per hour and 2 degrees centigrade per hour to go to 10,000. Sorry, 1,000 degrees centigrade. So basically, that will take a few days on the time scale, right?
No, actually, we did not go to 1,100. So I show you actually just 1 minute. So this one, na?
No. The making of the crystal, the that curve.
Okay.
Yeah, this one.
No, actually, it takes something like 12 to 14 days.
12 to 14
this
days.
cooling,
Okay.
because this cooling is 2 degrees centigrade, na? And increasing also like 15 degrees.
So why so slow? Like
yes, so slow cooling is important because we are allowing to grow this material inside a flux. So let's say I give you one easy example, that is copper sulfate crystal. So what we take, first we take copper sulfate powder, and we in a water we basically try to dissolve, and as we rise the temperature of this solution, we can basically dissolve more and more copper sulfate in water, in this water. So when we reach a supersaturated condition, then we allow the system to cool slowly so that it crystallizes very nicely, and it grows large size. So we have to allow the system to crystallize. So for crystallization and starting from the nucleation, we should give a larger time to grow these crystals. So that is the point. If you disturb, I mean, the first temperature cooling will not help in this case. So this is important for growing crystals. we should cool very slowly. Yes. So for this case, we went with 2 degrees centigrade per hour. So one can even go 1 degree or even, yes, slower. Yes.
So if I cool fast, like the crystal will break, or
yeah, so if you cool fast, you may get very small crystal, not a large size. Yes, that is one possibility, and sometime, yeah, sometime you may not get also.
okay. And how do you characterize the cleanliness of the crystal? Like, is there any direct way?
Cleanliness means
Like if there is like there are impurities.
yeah, so we check with our X-ray diffraction. So that X-ray diffraction pattern basically confirms whether there is any impurity or not. So if there is any kind of impurity or the flux element present in this case, then we would have seen other extra peak which are not coming from the particular this pattern or the particular this structure. So you can see there is no extra peak at all.
Yeah. Okay, I also don't have any more questions. Anyone else?
So I have a question. So
yes,
in these crystals, you also expect if it is odd number of layers, there will be Hall resistance, or
yeah. But for our case, it is bulk measurement completely. Means we don't have control over.
But if there are if you take an odd number of layers, we see. Right?
We are predicting, but we are not confirmed. Yeah.
Okay.
Yes. Yeah. Kind of like we are comparing with this AM and BI2T. That is the only point.
Thank you.
Yes. Thank you. Thank you.
Okay, so I guess no one has any more questions.
Any optical measurements done on this?
No. Yeah. Actually,
because the system is interesting. It has a lot of application for spintronic applications. Hey, is there any same kind of behavior at room temperature with low magnetic field?
Actually, it has antiferromagnetic transition 5.1K. So better if you want to see really interesting phenomena. I don't know actually at what time. I mean, whether you can see any interesting result at high temperature, but it has antiferromagnetic transition at 5.1K. So definitely you would see, I think, something interesting. I mean, if you go lower, not room temperature.
But above 5.1, is it ferromagnetic or?
No, it's paramagnetic.
Oh, this material will be very interesting for spintronic applications.
Yes.
Yeah, we can discuss this later.
Yeah.
Okay. Then if there are no more questions, let's thank virtually Souvik once more, and we join next week, I guess, from even by so hope you are so I'll keep you updated. So with that, I'll close the session, and thanks Souvik for joining and giving this wonderful talk today.
Thank you.
Okay, bye everyone then.
Bye.